In the past, we have learned about the change in enthalpy. For example, if you have a chemical reaction where the reactants have a lot of energy and it gives off energy and turns into products right here, this system would be exothermic, giving off heat. Okay. If you have another reaction where the reactants don't have that much energy and then they absorb energy and turn into products, okay, this would be endothermic. Which do you think is more likely to occur or is easier to occur? An exothermic process or an endothermic process? Yes, I think exothermic process would be easier because you are giving off energy, where endothermic you need energy. So it's easier to give away the energy, okay? Which would make a system a little bit easier to turn into products and a little bit more spontaneous. But that is not the whole story. You also have to look at entropy. So in this lesson, we will be learning about entropy. Okay, and entropy has something to do with the degree of chaos in the molecules. In this lesson, we will learn that in a system, if a system is exothermic, it is more likely to occur and more spontaneous. But also, you have to consider in a system, it is more likely to occur if it becomes more chaotic. Okay, for example, if you cleaned your room on a Sunday, it is when entropy hits by Friday, it will be very chaotic or very messy. So entropy has something to do with chaos. So let's look at this reaction right here. Here, you watched a video of barium hydroxide and ammonium nitrate. These are two solids which are very ordered. Okay, so ordered meaning the crystals have a certain formation. Okay, when you mix them together, the solution, the solid starts to make products. Okay, and at the same time, when they put water in between, the water froze. Is this endothermic or exothermic? Okay, so if the water on the outside of the beaker froze, that means the surroundings got cold. That means the heat went into the system. So this means that this is endothermic. So you might think, oh, that's probably not likely to occur because it's endothermic. Okay, because it's harder to take energy in than to give away energy. Okay, but still, this reaction was quite spontaneous. The reason it's spontaneous is because in the beginning it was ordered, and in the end it became more chaotic. As you can see in the products, you have aqueous solution, aqueous, and a liquid. Okay, so in these forms, the molecules are moving faster. There's a lot more of different types of molecules. Water is now considered a part of the system. So it is a lot more chaotic. Okay, so the reason this reaction was spontaneous is mostly because it tended towards more chaos. Okay, so we have laws of thermodynamics. The first law of thermodynamics states that energy is conserved. Okay, energy before is the same as the energy after. The second law of thermodynamics states that the universe tends towards more chaos. Tends towards more chaos. Or an increase in entropy. Therefore, if a system has a way to go towards more chaos or an increase in entropy, then the system will turn into products. Okay, so if you look at the definition of entropy, what is entropy? Here I have Superman hitting the concrete, and then you have a lot of different pieces. So that is a lot more chaotic than one piece of concrete. Okay, so entropy is a state of disorder. It is also the number as measured as the number of microstates. So you can imagine if you're taking a picture of one person, you can only get so many shots. But if you're taking a picture of 100 people, you can have many, many different shots, so many different positions. So think of entropy as number of positions, or we call them microstates. Okay? Entropy helps determine if a reaction is spontaneous. If it's going to tend towards more disorder, then it's likely going to be more spontaneous. The symbol for entropy is S, and that's why I have a picture of Superman there, so it helps you remember. The change in entropy is delta S. Okay, so let's think about this. How does entropy change if you go from liquid, solid, liquid to gas? So in the beginning, it's ordered as shown by this picture right here, and then it becomes a little bit more disordered as the molecules or particles are able to pass each other. And then in the gas phase, intermolecular forces are broken, and and the gas molecules have a lot of energy. Okay, so how do you think entropy changes? You're right, it goes from low to high. A solid has very low entropy because it's ordered, as you can see, the little circles ordered in this crystal lattice, while a gas has a lot of disorder. Okay, so as you go from solid to gas, the entropy goes up. Okay, in terms of delta S, if you're going to from um, solid to gas, and let's say this is 100 units of entropy and this is zero. Let's say this is zero. So the final minus initial is 100 minus zero. That is 100, which is positive. So if delta S is positive, that means it becomes more disordered. So what we want is a positive entropy to make the reaction more spontaneous, likely to be more spontaneous. Okay. And what are some ways we can increase entropy? One of them is to heat this up. Heating up the substance will give it more energy. Of course, they'll move faster, they'll vibrate, they'll rotate, and have more translational motion. You can also mix the substances, then that means it's more chaotic. Imagine one person versus two or three people, okay, in a party. You can also dissolve substances. So every time you put salt in water or sugar in water, it becomes more chaotic as well. And when the molecule becomes more complex, for example, which has a higher entropy, O2 or O3? Well, which is more complex? Of course, O3 is more complex because it has more atoms. Okay, here's another example, F2 or I2. Okay, as you can see, they both have the same number of atoms, but I2 is bigger. I2 has 53 electrons each, while F2 only has 9 electrons each. So this one is definitely more chaotic or more complex because it has more electrons. So you have to consider that as well. Okay, which has more energy, a solid, liquid, or gas? The gas, therefore, it has more entropy. Okay, so let's go ahead and look at this. Please pause the video and answer the following questions. Choose the member with a higher entropy and justify your answer. Just give a reason. Okay, 1 mole of SO2 or 1 mole of SO3? Definitely 1 mole of SO3 because it has 4 atoms versus 3. 4 atoms versus here it only has 3. 1 mole of CO2 or 1 mole of CO2? Oh, they're the same. Oh, but this one is a solid, this one is a gas. So definitely this one has more chaos, more microstates as the gas particles move with no intermolecular forces, and they're moving really fast. Letter C, 3 moles of oxygen gas, which is O2, or 2 moles of ozone, O3. So here you're kind of confused. Is it O2 or O3? Well, O3, I told you, is a more complex than O2, but you have 3 moles of this. You have to consider that first. 3 moles is 3 times 6.022 times 10 to 23. This is only 2 moles. So the answer would be the 3 moles of whatever substance. Consider the number of particles first. 1 mole of CF4 or 1 mole of CCl4. Okay, they have the same number of atoms, but fluorine is definitely smaller or has less electrons than chlorine. So this wins because chlorine has more electrons. And imagine those electrons moving around having more microstates or higher entropy.